Oh yeah. Okay, so welcome to this tutorial on how to influence and improve decisions through optimization models. It's my pleasure to introduce Professor Jeffrey Camm. Professor Camm is an Associate Dean of Business Analytics and also the Inmar Presidential Chair in Analytics at Wake Forest University School of Business. And I tried to summarize many of his achievements. So he was the editor-in-chief of our journal Interfaces. In 2016, he received the George Kimball Medal for his outstanding service to the profession. In 2017, he became Inform's Fellow, and he's a pretty well cited and pretty well recognized author in the area of application of optimization modeling to solving difficult problems in real life. So let's get started. I just want to give a piece of ad here. The recording of this tutorial is going to be available all together with the slides and the paper in the Inform's website in the future. So without, I'm not going to waste more of your time. So let's welcome the speaker.
Thank you. Great to be with you today. I'm going to stay down here rather than go up there, if that's okay. I hope we can have an interactive session rather than just me talking. So just shout out or flag me down or something if you have different experiences than what I'm going to talk about or something that you think will add to the talk that I've put together. I'd like to thank Doug for inviting me to be a part of the tutorial sessions here at Phoenix. And I'm probably going to be the least mathematical tutorial in the bunch, you think? Is that a fair statement? So let's be interactive if we can be. And I'm basically going to talk to you about what I've learned along the way through consulting and teaching at the university around optimization. So just a little bit of background. Everybody has different backgrounds, and so you have different biases when you come to anything, really. So this is my background. I have a BS in math from Xavier in Cincinnati, and then I went to a wonderful program at Clemson. Doug was one of my instructors back in the day, but there was a management science PhD program at Clemson. This is like 1980, which I think was way ahead of its time. I literally took half my courses in the math department and half my courses in the business school. And that kind of it set the stage for where my career went in terms of being very applied and always focusing on real problems and that sort of thing. I was at the University of Cincinnati for 31 years. It was a great fit for me. Showing a real lack of judgment. I was department head for like 20 years. I don't know why I did that, but it was a great group, and they were always really focused in an urban university, really focused on solving real problems, very applied. And then I actually moved to Wake Forest, retired from the Ohio system, moved to Wake Forest in 2015, so I've been there for about not quite 3.5 years, created a master's program there, led the creation of a master's program there. So it's exciting times to be in analytics or 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 whatever label you use. We could probably spend a whole session on that, but I won't deviate down that path. So I just want to make sure you realize I'm not just an academic that sits in my office and thinks up problems and tries to solve them. A lot of my publications are actually algorithmic. So somebody brings me a real problem that CPLEX or Gurobi or whatever has trouble solving in a fast enough time. And I usually would work with a PhD student, and we develop an algorithm that exploited the structure of a problem or developed a new algorithm based on what we could learn from the context. But I spent a lot of time. I had an LLC when I was at Cincinnati. Now I'm more of an administrator, so I shut it down. But it was called Z-Star Analytics. I don't even know if we use that anymore in the profession. Z-Star, so Z-Star Analytics. And these are some of the companies I worked with over the years when I had that LLC when I was back in Cincinnati. And usually it was supply chain design kind of optimization, but not always, but 90% of them. So some big companies there, some small companies there. And I've learned a lot along the way by working with companies. And so if you're an academic, let's take a show of hands. How many academics in the room? Probably a lot. Actually, not too bad. This is a pretty good mix of the stuff we were talking about at breakfast this morning. Academic and industry. So I learned a lot by working with companies. It impacted my research and it impacted my teaching. So
does that show that you consulted with Informs for optimization?
No, that's a great question. I guess loosely speaking, I did win the Kimball medal, so that counts as maybe working for Informs to some extent. That's a lot of service, but yeah, the others are legit, and the Informs is the slide template they gave me. Great question, Larry. Larry's on it. Larry's on it. Very good. So, interesting companies. Here's what I'd like to go through, and I hope to leave some time for questions, but please ask questions as we go along, or make comments as we go along. And I'm on a panel at 12:05, so the schedule gets kind of tight here. I think I'm supposed to 10:30 to 12, but I'll probably end a little early so I can run over to the other session. So, and some of this is not quite in the paper. All the good stuff's in the paper. I put some things on the front end here just around, there's this whole thing with analytics and operations research, and how do you kind of get your head around what's happening in the marketplace. So this is Inform's definition of analytics, which I think is actually the best I've seen. Yeah, so it's the scientific process of transforming data into insights for making better decisions. And I don't know, you can define operations research different ways, management science. My PhD's in management science. But at the end of the day, I think OR actually maps, or let me say it this way, analytics maps onto OR to my way of thinking, because OR has always been problem focused. If you look back at the origins of operations research, it was problem focused. It wasn't so tool focused as we got more academic maybe, but and I think that's where analytics is right now in the marketplace. And so you've probably seen this a million times. We try to categorize things into descriptive, predictive, prescriptive. And I get a little nervous because if you go back and read Gene Woolsey, how many people have ever heard the name Gene Woolsey? All right. There are even some young people who are raising their hands back there. That's pretty good. Gene Woolsey, other people who wrote, who are kind of around at the origins of OR, or at least the origins of ORSA and TIMS. They always talk about losing sight of problem solving in favor of algorithms and in favor of the tools. And so I've always tried to step back, even though I did algorithmic research, I always try to step back and stay focused on the problem. And I think that's one of the healthy things that's come out of this analytics movement, is there's a sort of a new focus, even in academia, on problem solving as opposed to just working on tools. I also have an opinion on how all this fits together, but so prescriptive analytics, everybody says, well, that's because you get a course of action to follow. That's what makes it prescriptive. And I think that's great. If you think about what's going on in that space, there's rule-based systems, and there's heuristics, and then there's how we, within the Informs community, we talk about optimization. And so I don't know if you can think of other things that are in AI can be bundled into all this stuff too, right, for optimization, but I would probably put most of that in the first two categories. So optimization is a piece of this. That's what I'm going to focus on today. And I'm actually going to take a fairly narrow focus that was aligned with my consulting over the years. So I'm going to stay, in the examples, I'm going to stay linear, and I'm going to stay deterministic. And so, there's obviously a lot more we could talk about. On rule-based systems, so to go back to the tools for a minute, so if you take a descriptive model like a data dashboard, if you put a rule on that, it becomes prescriptive, right? So think about a dashboard that has a quality control map, and you're tracking data, and all of a sudden you apply a rule to that where you have control bands, and if you have 3 straight observations outside of the control limits, you stop the machine. So you take a descriptive model and apply a rule to it, it becomes prescriptive. The same is true for some predictive models. If you have a logistic regression for credit scoring or whatever, and it predicts, the probability of a default. But now if you put a rule on top of that, a threshold, if Jeff's logistic regression has a probability of default above my hurdle, which happens to be like 0.3, then I don't give Jeff the loan. Now you've taken a predictive model, applied a rule, it becomes prescriptive. So I think it's further evidence, I'm hoping you agree with me, I'm pleading my case here, that at the end of the day, it's all about problem solving. No one just does a descriptive model and lets it go. No one does a predictive model and just lets it go. The end game is always about solving the problem. So that's always been my focus. And that's probably why I was in optimization, because it always winds up with, as we're going to see, maybe not an answer, but at least some suggestions from which you can choose, right? That's why I was attracted to optimization, I suppose. versus other kinds of analytics. So I don't want to bore you too much, but we're going to start from the premise that we have an optimization, a math program. It's a max problem. It can be a min problem. We all know that. I have some less than or equal to constraints, greater than or equal to constraints, equal to constraints. But I'm deterministic. That's all I'm really going to talk about today. So how do we train ourselves to build models? And I think if you think about how decisions are made, and this is in a lot of textbooks and a lot of papers, but how decisions are made leads us to how we think about, at least how I think about building optimization models. So, sort of very simple set of rules. What am I trying to decide? If I can't answer that, I have to go back and keep asking questions, right? What am I trying to decide? And by the way, managers don't really typically, in my experience, define the problem for you. What do managers give you? Symptoms of problems, right? So you have to be like a good doctor, a real doctor, an MD, as they say. They'll say our inventories are, we just merged with another company. We know our supply chain is out of whack now, and you have to keep asking questions to get to what the real problem is. So what am I trying to decide? What is my metric of solution quality? How am I restricted? That's how I think. And when I was younger, I thought everybody thinks that way, and they don't. They just don't think that way. But if you boil down a problem to where you can answer these three questions, you could probably build a math program of it. You might not be able to solve the math program. You might not be able to get the data. But this, I call it an optimization mindset. That's how OR people tend to think. And I think we often assume other people think like we do. So I'm going to go through a series of examples that I've used in teaching. This goes way back actually to Lynn Deering at Clemson in the 80s. He had a consulting project. We've changed the name to Protect the Innocent, but the bottom line is I want to run through this little example with you, and we'll use it a couple of times in the talk today. So this is CALHOUN Mills. We wrote a paper on it years ago. I think it's in IIE Transactions. You can look up. It's like a little case. So we have 15 fabrics. We have a demand. We know the demand with certainty. So we're in a contract situation where we know the demand in yards of each of these 15 fabrics. We have Dobby looms and regular looms. Regular looms cannot make the first four types of fabric, so you'll see X's there. But Dobby loom can make any of these fabrics. We have the yards per hour. We have the mill cost, that is if we run it inside, and we have the outsource cost. What does it cost if we don't have capacity to go outside and produce what we need to meet the contract obligations? We have 90 regular looms and 15 Dobby looms. So far, so good? Everybody understand the problem? Make versus buy. Pretty straightforward problem. So what am I trying to decide? How much of each fabric to produce in-house and how much to outsource? What's my metric of solution quality? Cost. How am I restricted? I have to meet demand. I have limited resources to meet the demand. I have infinite capacity, presumably, in outsourcing. So far, so good? All right. So we can define some data, and we have variables, and I can build a model. So what is it? This is a linear program. We'll assume we can have fractions of fabric. That might not be good, but we're going to assume it. The first term in the objective function is the inside cost if we produce. Little r is how much of fabric I produce on a regular loom. D sub I is how much I produce on a Dobby. OI is how much I outsource of fabric I. And we're going to assume it's continuous and we can just do whatever we want in terms of splitting orders and everything. So first set of constraints, turns out if you take, are there still 7 days in a week? 7 days in a week times 24 hours in a day times 90 looms gives you 196,560 loom hours of regular type. And the left-hand side of that constraint is how much loom time of regular type is consumed based on what we make. Same thing for constraint 3 there. That's Dobby hours. And then I have to meet demand in constraint 4. And I can't make the first 4 fabrics on a regular loom, so I lock them out. And I have non-negativity. So far, so good? Everybody's on board? Simple linear program. What do we expect from this model? So the model I built, I'm just going to ask this simple question. What do we expect to happen when so when you build a model, you should have, if you know the data and you know the problem context, you should have some expectations about what's going to happen when you solve the model, right? So before I go on, are we good with the model? You have like a mental map in your head, so I can go back to a previous slide. Minimize cost, can't exceed Dobby hours, can't exceed regular hours, got to meet demand. You have to lock out the first 4 fabrics. Go back to the data. What do we learn just from looking at the data? Just take a look and see if you can figure something out that would give you some intuition about how this model is going to behave. I'll lead the witness. What's true about inside cost versus outside cost? Outside cost is always more expensive, right? So if I solve that simple model that I created, what's going to happen? Outside cost is always more expensive. What if I get back a solution that has leftover loom hours of some type, and I'm also sending something outside? That's not going to happen. You see where I'm going? You got to think about the model. What do you expect? How do you expect that model to behave? I might solve the problem and have leftover loom hours and nothing gets sent outside, and I feel pretty good about that. But if I'm sending something out and I still have even 10 minutes left, it's a continuous model. You would always make it inside, right? So I have some expectations now that if I run this model, either I'm going to have leftover loom hours, in which case everything's probably made inside and I'm good. I have enough capacity, although I ignored some important things here, right? Like there's time it takes to change over a loom, for example. By the way, I'm also not solving the production scheduling problem here. I'm not going to tell you loom 7 should be on Tuesday making fabric 9. I'm just trying to figure out what I should make and what I should buy. So I built a model to answer that question, not something more than that. So if we go back out to the model, what we expect from it, this is the solution. It costs $599,108.16. It's minimized cost. All loom hours are consumed, and I send fabric 6 outside, some fraction of fabric 6. And we have fractions flying around, so to really get to, we'd have to do some adjusting, solve some other models. We can talk about that, but fabric 6 is the only fabric that is sent outside, and all the loom time is consumed. So at a high level, I think I could explain to a manager we need more capacity, otherwise we're going to have to go outside. We're going to come back to why fabric 6, so I want you to think about that. We'll come back to that later. I can go back to the data, but be thinking about, don't shout out the answer yet if you know it, but be thinking about what, if you just had to give somebody a rule, what would you send outside, okay? What does your intuition say? Which fabrics, if you run out of capacity, which fabrics will be sent outside? Because if you give this solution to a manager, he or she is going to ask, that's going to be the first question they ask. They're going to say, why is fabric 6 going outside? And if you don't have an answer for that,
it must have to do with the marginal cost of outsourcing versus insourcing.
it does. But hold that thought. It's exactly. But this is a beautiful example because I think it explains linear programming at its most fundamental level. So I'll come back. Hold on to that, Larry. I can see your wheel spinning, man. Don't shout it out when you get the whole story. We could put integer constraints on this, right? Now it's really hard to solve. I got tired of waiting in solver, so I don't have the answer for you, but it's going to take a while to solve that with a general integer as a general integer problem. But how else could we extend that model? Well, in reality is we probably want to commit, we're going to make this all on Dobby looms, or maybe we want to do this all on regular looms, or all outsourced. Make it a binary choice as to how we make a particular fabric. So we can add some linkage constraints, right? You see what I've done here? I defined 3 sets of binary variables that are binary. So we're going to extend the linear program to where it becomes a mixed integer with binary variables. And I'm saying there are different ways you can do this. In 11, I'm just saying, look, you have to make a choice for a fabric. You're going to make it on regular Dobby or outsource. Make a choice. And then it turns on a binary variable in 8, 9, and 10, or it locks it down to 0, and so you can't make it. If you didn't choose that, you can't make it. So those are, usually we refer to those as linkage constraints, where you have a binary variable on the right-hand side. I have the demand there, so that's because we're going to make all or nothing. We're minimizing cost. If you lock the other 2 out, it's all going to go to the third. So it all works logically. But what do we expect to happen now? Now we have a new model. The old model with these capacity linked to binary, demand linked to binary, I'm only letting you choose one option for each fabric. Are the statements I previously made still true? I.e., I have to, if I use up all my if I go outside, I have to use up all my capacity. No, because now we've turned it into a discrete problem. And it could very well be that the optimal thing to do is to have capacity left over and send something out, right? In fact, you have to do that, right?
Because you don't have enough internal capacity to do the entire job.
Exactly. So now it's a building block problem, right? It's a building block problem. You have to trying to figure out how to fit things together. So don't expect this model to behave the same way the linear program does when it's in continuous space. So this is actually the solution to that problem, where each fabric you have to do in a certain way. We have a benchmark. I'm going to talk a little later about benchmarking. What did we say before? 509,000 or something like that, or 590,000, whatever it was. We're up to 611, and we have Dobby and regular hours left over. How do you explain that to a manager? That's a little bit more involved because we have to do all or nothing. It might be that we're just going to have leftover loom hours. That's a harder sell, though, right? Than in continuous space. Okay. So I'm gonna switch gears here now. I think most people think about, to go back, map it back to descriptive, predictive, prescriptive analytics. You know, I'm talking to students, I'm talking to employers. Most of them say, a lot of the work that's being done is in those first two buckets and not so much being done in prescriptive analytics, right? And so I'm trying to figure out why that is. You read all these things about, well, as a company gets more analytically mature, they'll discover optimization and all the stuff we do. And that might be part of it. But I wonder if some of it is that by definition almost, when we build an optimization model, we think, here's the answer. Gave us the answer. And I'm going to argue that we should use optimization models more like we use simulation models. Even though I'm completely in deterministic space in all these examples. So what do I mean when I say we should use optimization like simulation? You don't just build a model, find an answer, hand it in, right? That's what we do in class too many times, unfortunately. But how can you use that model to generate alternatives for the client? And I have some real examples I can talk about. So using that model in an experimental way, and maybe even not even changing the data, but looking at more than just the optimal solution from your model, okay? So that's where I'm going. And one of those types of things are alternative optima. So,
Jeff, it's always nice to let a manager think that he or she has a choice.
Exactly. One of the, the illusion, and sometimes, well, in my consulting started with a big project. I was extremely fortunate, a project with Procter & Gamble back in the early 90s. And it was to redesign their North American supply chain. So Canada, US, Mexico, clean sheet, you know, in theory a clean sheet. We want to know which products should be made at which plants should be open and closed, where should the distribution centers be, so that we ensure customer service, all to minimize cost, meet service requirements. Very high strategic level model. And I, as a young assistant professor at the time, thought, at the time it was MPSX or something, I'm going to build this mammoth model and crank this thing out. We didn't do any of that. It's pretty innovative for the early 90s. On a laptop, this guy Franz Dill, some of you might know Franz from P&G, we created a mapping system where the product managers could go in and lock some things in, and then a network flow optimization that was really fast would go behind the scenes, so we didn't have to wait for an integer program. It made like 1,000 runs of that model, and then pulled all the product category teams together and negotiated a final supply chain. And so because there was buy-in, there had to be buy-in from the product category managers. That project saved $250 million a year for Procter & Gamble. I joke with my students, some of them are here, I only got 10% of that. I didn't get 10% of that. It was the most cost-effective project ever done. Also involved like 500 people, but anyway. Back to CALHOUN Mills, I digress. CALHOUN Mills, remember we just solved that problem, so I'm going back to the continuous problem. I'm getting away from the binary variables. So going back to the continuous problem. Think about the non-basic. So how do you get in a linear program an alternative optimal solution, an alternative optimal solution? What do all the textbooks say, including mine? Go ahead, Larry.
I don't know what all the textbooks say, but you would find the optimal value of the target cell, and then you would add a constraint that the target cell has to equal that, and you would maximize or minimize something else.
Yeah, what the books say are something like, assume you don't have degeneracy and find a zero reduced cost, right? And then figure out what to do next. You and I grew up with the spreadsheet revolution, so that's how we do things now. And that's what this is. So this, what I'm going to show you is a model that will give you an alternative optimal solution if one exists, but it's not looking at to see where the zero reduced cost is in a non-degenerate solution, blah, 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 blah. If you know how to model, you can do just about anything you want if you think it through, right? So what do? I'm doing exactly what Larry just said. I'm taking the old objective function, making it a constraint, setting it equal to the optimal value we found. And I'm taking just the non-basic variables, make that the objective function, maximize it. If this comes back positive, I found a new solution that's optimal, that in some sense is as different as possible in a summation kind of way from the original solution that I found. And you can do other things like, maybe I want to make D3 as big as possible. Put that in the objective function instead of this, right? So if you know how to model, you don't have to worry about all that other stuff that you learned when you were learning the simplex algorithm. And what does it mean to be degenerate, and what does it mean to when you have a zero reduced cost in a non-degenerate situation. Anyway, for a non-basic variable. So if you know how to model, you know how to do a lot of things. If we solve this, now I have a different solution. That in the summation of the non-basics is as different as it can be from the original solution that I found. So now I have an alternative. I can show a manager two different things. And the manager has a choice. Maybe there's some reason why one of these is better than the other. And there might be others, right? I just found one that maximizes the sum of the non-basics. But there might be there could be a lot of alternative optima. In fact, if you go back to the data, did anybody look hard at the data? What was true about the production rates? Yeah, the production rates, if you look down those two columns, are always the same. So it shouldn't be surprising. There are probably a lot of alternative optima. That's why we only had one inside mill cost. The production rates were the same on each type of machine once you got past the first 4 fabrics. If you go back and look at the data, you should look at the data, I think, before you hit solve, but go back and look at the data and try to figure out why you get the answers you get. We're still sending fabric 6 out, so remember that. The more interesting case, and I can state unequivocally, this is the single most valuable thing I learned after graduate school. My colleague at Cincinnati, Dennis Sweeney, when we were working on the Procter & Gamble project, said there's this little thing in a SciAm journal that a lot of people don't know about, but I've used it, and we use it in the following context. I was talking about before that laptop solution to the P&G supply chain problem. We didn't have time to solve the assignment of DCs to customers, that problem. So what Dennis showed me how to do, which is in this paper by Bollis and Jaroslaw, is you can generate a family of solutions based on binary choices. And so what we did was we developed like the top 25 structures of the supply chain from DC to customer and put them in a table. So when the product category manager started clicking on locking things in the supply chain, then we could do a table lookup. It wasn't solving the IP anymore, it was just a table lookup. And so it was very fast. So that's how I learned this, but I'm going to explain to you how I've used it for 15 years in consulting and why I think it's valuable. So if you solve a binary integer program, or if it could be mixed integer and you're just focused on the binary part, the binary choices, the flows come after that. So you just create two sets. I'll call them O and Z. O is the index set of the binary variables that turned out to be 1, just the index set. Z is the index set of those that turned out to be 0. Then if you add this constraint, the beauty of it is it only cuts off one point. It's the point that was optimal, and everything else stays feasible. So if I append this constraint and resolve, I'll get the next best solution, okay? If you think about the constraint, it basically says if you keep everything, then you have to turn something else on that wasn't on before, or you can drop some of those that were on and you'll be fine.
For this approach, you'll get one of the many possible second best solutions, right?
Stay with me. Yep. And the beauty of this is it's iterative. So I can apply it, I can get a solution, apply this constraint, I'll get the a second best solution, or it could be an alternative optima, right? If I append this constraint and I get back the same objective function value, what have I found? A new solution, alternative optima. As soon as my objective function degrades, I know I found a second best solution, but there could be 100 of those, right? But you keep the constraints you appended and keep doing that. Now it might slow down the optimization because you're appending constraints, but it's iterative and cumulative. And so you can generate a family of alternative optima solutions if they exist. You can generate, I'll talk more about how I use this, but I had a client who I used to refer to as my David Letterman client, because every time I solved a problem, he said, I want the top 10 solutions. And so I did that every time. I appended 9 constraints, I gave him the top 10 solutions. And now you're giving more information. And again, to map it back to how we think about optimization, it's presumptuous, I think, to say, here's the answer, right? So if you can generate alternatives with optimization models, you know, now you're talking to management in a little more flexible way, and let them choose. Obviously, when we're building models, the models don't contain all the details, and I'll map back to that in a little bit with a real example from my consulting. So if you walk away with just one thing, and if you solve optimization models, this is what I hope you take away from this tutorial. That I have a paper in Interfaces a few years back that is referenced in this paper in the tutorials, but it's called a short course in suboptimization. And it's basically this, that you can generate suboptimal solutions to a binary integer program by simply applying, you don't have to write your own branch and bound code or anything, apply this constraint, use whatever solver you're using, and you can generate the top 10 or top 50 or whatever you want to do. So here's an example, I think, that illustrates this, just so you have an example. This is an old example from Dennis Sweeney back in Cincinnati. In 1979, the banking laws in Ohio changed. I love this problem because it's a real problem, and it's like somebody wrote it for a textbook. It's very clean. So it used to be that if you had what's called a principal place of business, what you can think of as a branch of a bank that clears checks, it could be more than that, but the law stated if you had a principal place of business in a county, you could put branches in that county. So Cincinnati's here in Hamilton County on the Ohio River. The old law was if you wanted to have branches in Hamilton County, you had to put a principal place of business there first. In 79, they changed the law, and they said you can put a principal place of business in a county, and then any county that it touches is also fair game if it shares a border, right? So what's the problem that this out-of-state bank asked Dennis Sweeney to solve back in the late 70s? Well, if we wanted to open Ohio wide open to our branches, where should these principal places of business be, and how many do we need? It's a set cover problem, right? A classic example of a set cover problem where the A matrix is, do you share a border between counties or not, right? So that's an example of the new law. If I put a principal place of business in the lower left, the southwest corner, then all those blue counties are now open to my branches. And so here's a set cover model. There are 88 counties in Ohio. I put some numbers on them so I have a frame of reference. You can solve this problem very fast. And here's a solution. So you have to go back and look at where my numbers were on the map, but it turns out it takes 15 principal places of business to cover every county in Ohio. And now if I want to append one of those, the constraint I was talking about, I take those that turned out to be 1s minus those that turned out to be 0, and this solution is less than or equal to 15 minus 1 is 4. Remember, my objective was to minimize the number of these things. So there are 15 up there in the set O. 14 is the right-hand side. You apply that, and now you get a second best solution. It turns out if you do that again, there are 3 alternative optima that give you 15. And what I've done is circled up in the northwest corner how these solutions are different. But I could keep going. The next one will give you 16, right? And there are probably a whole bunch of 16 solutions, but there might be reasons why one of these solutions are better than another. Now you might say, well, if there are reasons why one solution is better than another, you should put that in the model. I think that's a fair argument. But if you're starting the analysis and learning as you go, I think this is a pretty good way to understand what's happening. And it has that characteristic that I'm not just giving an answer anymore. of giving alternatives. And I can remember when I was first got my hands on this example, I was hiking with a friend of mine from high school. He's a marketing person. And I was, for whatever reason, we must have been really bored. I was telling him about this problem as we walked along the trail. And I said, how would you solve this problem? And he described a greedy heuristic to me. And it took me like the rest of the hike to explain to him why a greedy heuristic might not be optimal, right? But I used to give this problem to my students literally with a sheet of paper. And I'd say, take your pencil, go for it. So what your natural thing to do is pick a county that has a technical term, boatload of counties around it, put a dot there, shade them all in, and go again. And then you find out you have all these missing links, and you have to go back in and paint them all in, and you wind up with like 25 or something. But there are counterintuitive things here. Like you see counties that are chosen that are on the border, right? Which you probably wouldn't do if you were using a heuristic. Just visually, you'd gravitate towards the middle, right? So I think it's good. This is a good example because it's so visual. And if you give this to a manager, you can see how the pieces of the puzzle fit together and at least explain that while we as humans can't just look at this and find the answer, the power of optimization is it can, and it doesn't look at all possible combinations. It's smarter than that. So anytime you can do something visually, that whole 1,000-word thing is true.
Like
Western Airlines?
Examples that problem with minimize hub location.
Hub location problem. Yep, same kind of thing. Exactly.
And in that problem, usually optimal solutions are like Boston, Seattle, and Salt Lake.
Right. Yeah.
None of the students can predict this.
Yep. Yep. Same structure and everything. Absolutely. Excellent. Yes.
How do you explain to a practitioner the combinatorial nature of the problem?
The
combinatorial nature.
Yeah.
The greedy thing is not optimal. How do you explain that to a practitioner and convince them?
Yeah, there are some good examples of that are out like on the internet that talk, well, it just gives them examples. It doesn't really explain it, but it shows how things explode, But, I guess in the past when I've tried to do that, either with students or with clients, you can talk about, they understand loops, and, they kind of get what a loop is inside a program. And if you talk about how I would change this, now I have to change the next one. And how long that might, suppose each one of these takes 1/10 of a second, and then just do the math, and they get it a little bit. But sometimes that's a challenge. Combinatorics is a challenge for clients. Other questions before we keep bringing the questions, comments? This is good. So now I'm going to switch. I'm going to use the same technology, but I'm going to talk about families of solutions. So same idea. I'm going to apply that cut, but all I did was in the Ohio banking problem case was I said there are 3 alternative optima, right? So how to use this when you're trying to generate family solutions, which is how it would be if we're, I think, treating this more like simulation rather than just here's the answer kind of thing. So this is just a point cut and paste from the paper that's in the tutorial book. But let me tell you a story that is in that other paper in interfaces. So I was doing some consulting work, probably early 2000s. It was a medical device company that manufactures in the U.S. and they wanted us to look at their distribution network in Europe. So they had distribution centers, DCs, in Europe. They had 5 of them, but all the product was produced in the U.S. So you had to get it across the water, send it out to the DCs, and then from the DCs to the customers. So manufacturing was not part of the study. It was just the distribution network in Europe. So we built a model. You can think about what that model looks like. It's a binary program, right? It assigns customers to DCs. You can vary the number of DCs that are open or closed to get the network size. We had the current DCs in the data set along with a whole bunch of other alternative locations. Pretty intense to go out and get freight rates and everything for sites you don't have, but you want to put it into the model. So there's a lot of data collection. It's a little bit more challenging, at least we found it a little bit more challenging in Europe than it is in the US. And so Jeff solves this network. I know, and it turns out we looked at something like 10 DCs open, 9, 8, 7, 6, 5, 4, 3, and looked at, think about that curve as you had, we don't have fixed costs in this model, by the way. I'm going to sidestep for a minute. I've been doing these kind of models with clients for a long time. They very rarely are willing to tell me a fixed cost value. they'll say, show me how variable cost changes, and my gut will tell me when to stop on that trade-off curve between how many locations you have open and you know, how the variable cost drops because you're closer to the customer, et cetera. Does that make sense? So this model does not have fixed cost in it. So I vary the network size, and it looks like 5 is about right. So there's an elbow in that curve of cost and number of open distribution centers at about 5, so that it seems like their network size is right. And then I generated like the top 10 solutions for a 5 DC network. The savings in the original solution, the one that was optimal for 5 DCs, had a savings of about 14%, which is actually pretty high for outbound from DC to customer. And it had, I think 4, it's in the paper, I'm not remembering it exactly, something like 3 or 4 of the 5 DCs were not current locations, and 1 or 2 were. Okay, so they were at 5. I found an optimal solution that looks like 5's good, but 3 or 4, I can't remember, of their DCs would be new. I didn't have transition costs in this model, right? So when I generated a second best solution, cost only increased by less than 1%. And guess what happened? 4 of the current DCs were in that second best solution, 4 of them. So which solution did they go with? You can swap out 3 or 4 DCs and get your full 14% savings. That's just a projection anyway, right? Or I can keep 4 and add one new one, and I give up it was like 0.3% or something. So something can be optimal by a lot or optimal by a little, and if you don't look around, how are you going to make a recommendation to your client that's really, you know, where you're giving them their money's worth? So you have to look at how optimal something is if you're going to recommend it. And so they went with the second best solution, which was all I have to do is swap out 1 DC. Think about if you had to shut down of 5 DCs, 3 or 4 of those. The inventory implications of that as you ramp up the other sites, the disruption and all that, was a no-brainer. If you just hit solve and gave them the answer, you'd never know that. So I don't teach that way anymore. For those of you that are academics, one of the first things I teach is how do you add these constraints and explore alternatives, so you're not just giving somebody an answer that might be optimal by a nickel and not know what's going on outside the model, right? Make sense? All right. So that's family of solutions. So now we're going to go really soft. I don't like that term, soft skills. Go ahead.
Just comment. This reminds me the fairness in resource allocation problems. The fairness.
Yes, fair, exactly.
For instance, in airline companies, we are trying to minimize the delay.
Yep.
But in the optimal solution, when we look at the total delay, it is not distributed among the airline companies
Right.
in a fair way.
That,
But when we look at the suboptimal solutions, we have more balanced delay reductions.
exactly. Yep, absolutely. Also, it's related to, if you've read, I don't know if Jerry is here, Jerry Brown, persistence. He's written a lot about persistence of, basically, if you're really deploying a model and it's running in real time. So I don't have a whole lot in this talk about what if you actually have to deploy a model where it's going to be running all the time. These are more one-off projects. But would you really rerun something that was radically different than the last time? Would you accept something that's radically different than the last time period? Just because it might be optimal by 0.1% and it's radically different from what you did last week. You wouldn't do that. So there's this idea of persistence where you say some percentage of things have to stay the same and then you solve, right? So it's all related to that as well. How are we doing on time? Not too bad. We're good. So I've been thinking a lot as I get older. Most of my research was around algorithms and stuff. And when I was younger in my career, there were people like Russ Akoff and Gene Woolsey who were always saying, you folks are all focused on the wrong stuff. You're always trying to get that 0.2 seconds off the algorithm, but what does it really take to get somebody to implement what you're doing? And so I've been thinking more about that as I get older, and now I realize I'm the old complaining guy. So for what it is what it is, but that's where I'm going. So there's a really good book called Storytelling with Data. Anybody know that book? By Nicole Cole Knaflack Nussbaum. Probably the best book about data visualization and storytelling combined. Really good book. But it talks about, if you want to get your point across, first of all, you better know who your audience is. That's kind of self-evident, but it's like putting comments in your code. Yeah, you know you should know that, but you don't do it, right? You just keep coding. So know who your audience is, know what your message is, right? And Cole says, you think just, and this is other places, she didn't patent this or anything, but think about it as 3 acts. 3-act play. Every time you're presenting, you're trying to, it could be peer-to-peer, you're trying to convince your colleague about what you've done, or it could be you're trying to convince an executive to implement what you're talking about. But think of it as a 3-act play. And you have to set up, what's the tension? Why do we even have a problem? How are we going to solve it, and then what, right? That's what this really says. Act 1, Act 2, Act 3. Calhoun Mills has it. We're going to go back to the Calhoun Mills problem. They have 15 fabrics, revenues fixed by contracts. Calhoun seeks a way to meet demand at minimal cost. That's the problem. And you could also say the question is, do we have enough capacity or not? Because we looked at the data. It says that, if you run the model, or if you actually just do some algebra or do some arithmetic, you can see you're not going to have capacity. So the stress is, or the thing that has to be resolved in Act 2 is, we don't have enough capacity. So we're going to have to outsource something, and what should go outside. And we resolve that by solving and finding that optimal solution, or providing alternative optimal, the way we talked about that when we're looking at that linear program. So just organizing your thoughts this way. What's the situation? Why is there a problem? What's the stress? Why were you called? And then how are you relieving that stress? That's what it comes down to. So I just have a couple of slides. So this is, if you look at the data visualization, not so much from a data exploration point of view, but from the communication point of view. And I have a paper in Interfaces recently on this with a couple of colleagues. It's common sense. Keep things simple. Don't have a lot of junk flying around on your slide, right? Know your audience. Use color purposefully. All these kind of basic rules that, again, make sense, but nobody follows them because, well, for several reasons. You don't have time, you don't think about it, or you have Tableau or SAS showing you these 3-dimensional pie charts that look great, but they blow up your message. You can't, you're better to have maybe a bar chart instead of a pie chart. So think about your display is what I'm trying to say. So this is just some verbiage there. You can read that. So the second act, we don't have enough loom capacity, so we're stressed. We know we have to meet the contract obligations, but we're not going to be able to do all that in-house. So how are we going to resolve that? And notice what I've done here. I've quantified some of the things we noticed in the data, so the client knows I haven't just run off and done my thing, but I understand the situation. I've looked at the data. The client might not know these things. So the average difference between inside and outside cost is 16 cents per yard. If we can make everything in-house, it would cost if we could make everything in-house, it'd be $585,216. What did I do there? I took my model, I took away the capacity constraints, and I ran it, right? If we had to outsource everything, how much would it be? So now at least the client has a range expectation. Again, I'm not just giving, here's the optimal solution. Trust me, it may or may not be a big deal for you, but you have to give them a range, a context in which you're giving them an answer. And this is just a little graphic that shows, a bar chart that shows the percentage that go to, and we could put this in color to make it burst out a little bit, but Dobby, regular, and outsource. So the striped is the outsource, it's only Fabric 6. And now I'm going to pause and ask you, why Fabric 6? And if it's helpful, I'll go back to the spreadsheet if you want to see the data again. Larry's in the hunt. Larry said it has to have something to do with marginal cost, the penalty for going outside, right?
And the marginal and the incremental time to make the fabric in question.
Bingo. So did everybody hear that? Here's how you can explain Fabric 6 is going outside. Most students in my class, when I ask them this question, they say, I want to see where the biggest penalty is for going out. So they subtract those two columns, and they find out Fabric 6 is not the biggest penalty. Or the smallest penalty, rather. Smallest penalty for going outside. It's not the smallest.
Ratio of the savings in cost and the extra time, like the knapsack twist.
Outstanding. Everybody hear that? If you look at the penalty per loom hour, Fabric 6 is the cheapest on a per loom hour basis. Isn't that the whole point of constrained optimization? You can't just look at the objective function. You have to know what's going on in terms of resources. So if you take the inside cost minus or the outside cost minus the inside cost and divide to put it on by the production rate to put it on a dollar penalty per loom hour, remember the rates were the same regardless of Dobby and regular, you'll see Fabric 6 has the smallest penalty per loom hour. And if you wanted to develop a heuristic, what would it be? Look for small differences in cost, but also those that are hogging the machine, right? Or you can literally say to a manager, this is more of a tactical level model. Well, if you want a rule, what you should do is take your spreadsheet, take the inside cost minus the outside cost, divide by the production rate, get it on an hourly basis, and then rank order those. And then if you find out you're not going to have capacity, you know, if a machine breaks down, now you have a pecking order to what you should send out to get outsourced, right? So we've learned something by solving the optimization model. We have, in a sense, because we had to explain it to a manager why we're sending Fabric 6 outside, we've created an insight that could be implemented without integer or linear programming. So there's some learning there in addition to giving them an optimal solution. Everybody with me? Yes, Rishi. I mean, if it's a massive problem, how do you explain it? Yeah, you have to, well, so many problems that I've worked on have been geographic that I've been fortunate, right? But you have to find a way to display things which might involve reducing dimensionality so that a manager can get it, right? But it's also true that they're going to be, these are pretty simple examples. They're real, but they're simple and intuitive, which is why I use them. But you could certainly have a problem that's, the answer comes back as not intuitive at all. Then what I would do is use a model to lock things down or not and show at least that my model says that it would be different by this much if I don't do this, right? So benchmark in a way by using your model creatively again. Other questions?
From here, for like multi-objective?
Yeah, that's another thing you can do is a multi-objective, even if you're not trading off, showing how as you focus on one objective, what happens to the other one, right? That trade-off curve. Absolutely. That's all related to family of solutions as well and all that. You know, looking at that trade-off and giving the manager a choice. Yep, absolutely. Yes?
So, in this, how do you deal with like the math is not declaratory kind of problem on this?
The
math is not declaratory.
What do you, tell me what you mean by that so I can.
Representation of the problem is probably not a real life.
I want to make sure I'm connecting with you. So you can show a graph as opposed to a map, for example.
No, it's kind of an analogy. The idea that you go through this process, you deal with the manager, you deal with it, but there's something you're not seeing either in the human process or the real world, kind of even the behavioral economics of it all, what's going on in that situation.
Right. I'm going to get to implementation in a few slides. Let me see if I address some of the issue there. It's sort of what you're talking about is like the last mile. How do you get it across the line, right? Very important stuff, obviously. So I do have something to say. This just shows that what I just said before. If you put it on a per loom hour basis, Fabric 6 is the smallest. So what do I recommend? A 3-act play. What's the situation? What's the stressor? What's the stress relief? Demystify your recommendation if you can. To reach each point, it might be so complex that you can't get the intuition. But you can, again, tinker with the model and show if you don't do this, what the model says will happen. So, benchmarking. This is one of those things that seems very obvious, but maybe we don't teach it enough. So, if you're working for a client, you better have some measure of what value you potentially are adding, right? And this is the kind of stuff, my approach to this has evolved over clients, but when I'm doing a supply chain design problem, this is what I do almost every time. I'll have a current baseline. What does that mean? I build a mathematical model. I actually use Ample and Gurobi or Cplex or whatever the client has. But I build the algebra, I build the model, and then they have data, and they give me the data, and I just lock it down in my model. I use the model as a big calculator. and I give them here's what it says cost is. In my experience, if it's within plus or minus 10% of what the accountants say, they're good. They say, use your model, go ahead. If it's not, then when there's something wrong, we made some bad assumptions, or we got some bad data. But that's the current baseline. What they're currently, last year's data, lock it in your model. You have a cost. What is that number? Then, some people don't do this. I'll do an optimized baseline. What do I mean by that? I'll keep their current facilities locked in and just optimize the flows and see if they're saving. In other words, they could have savings just by changing the management of their network and not have to do any capital investment in terms of facilities moving. Right? Everybody get that? Lock down, essentially, to put in our lingo, lock down the binary variables and solve. Lock down the binary to the current. And they've given me projected data. So it might be typically it's 5 years out, 5-year projection if you're doing a supply chain problem, but it could be further out. You might have scenarios to hedge against uncertainty, right? So you might solve different scenarios, but I lock that. What do I do there? I lock down their current facilities, but I give them the capacity they want, and I solve. So that's a current future baseline. If you don't change your facilities, your structure, but you might add capacity here and there, but you have future demand, what would you do if I wasn't on the case, right? That's what that amounts to. And then I just open it up and optimize. So my value is actually, they might be able to implement something fast, current to optimized baseline, or what's the long-term potential savings in the future baseline, the difference between that and the optimized future. Make sense? So you have to have these baselines to basically prove your value or the potential value of your work. I had one offer in the spirit of Gene Woolsey. I had one offer in my 15 or 20 years of doing this where a company called, a big company, Fortune 500 company, and I guess they were having cash flow issues in this particular department, and the guy said, would you work on a percentage of savings basis? And he must have heard my smile. I said, yes, sir, I'll work on a percentage of savings basis. And then we started talking on and on, and he went to his boss, and his boss apparently was more quantitative than the person I was talking to on the phone, and said, no, we're not going to do that. So I didn't get that job. But if you ever, we had a student at Cincinnati, operations management student actually, who went to a university. I can't reveal too much data, but went to a university, was there maybe just a year, and met this person at a company. And we always talked about this kind of stuff at Cincinnati. And he did this project, and all I remember was he said he did one project, and he paid cash for his house. It's a brand new graduate, PhD graduate. I don't know what he's doing now. He's probably on an island somewhere. This is some real data from a client I won't give you, but just to put some numbers to, this is not a really huge company or anything, but so I saw the current baseline was about 213 million. If I optimize the flows, now there might be reasons why their flows aren't, but what you can do is take what they're doing now and map that, and if you see arcs crossing in the supply chain, flows, you're like, what's going on? It should look more like a hub and spoke airline, right? And so here, there was like, what is that? A little over 2 million potential savings without investing in new facilities or changing the facilities per se. The future baseline, so this was probably 5 years out with demand projected, 248 million, and the future optimized is about 230 million. If they, and that didn't include now the construction of the facilities or anything. Remember I told you, they said we'll just look at the variable cost change, and when I see that I'm not going to be able to get a new facility for the delta, I'm going to say stop. So this is all variable. Inventory and transportation costs essentially. So that's benchmarking. Implementation. So I have a colleague, he's on our advisory board, Ben Martin's his name, he's at Haynesbrand, which is in Winston-Salem, where I am. I like this quote. Remember our definition of analytics way back in the beginning of the talk, but Ben is very pragmatic. He says insights without implementation are just fun and interesting facts. And he's right. If you're doing a project for Ben, he'll say, tell me how this is going to decrease cost or increase revenue or help me with service. If you can't answer that question, we're not doing this project. So we're not doing, just stuff for fun. So I think that's where you need to be with implementation. So if your work doesn't get implemented, if you don't factor in, you know, beyond the model and what has to actually change inside the organization, you're not going to add any value. So this is admittedly a trivial kind of toy example, but let's go back to the Ohio banking problem. We solved the set cover problem. The answer is 15. We'll be able to put branches anywhere we want if we put those PPBs in those 15 places. If you're interested in implementation, you can't just hand that to a manager. A manager's going to say, well, that's fine. I can't put down 15 PPBs now. Give me a glide path to where I'll eventually be at 15, but what order should I put those in, right? You can't just give somebody an answer like that. So you have to think about how can you use your model, or maybe a different model, to give a manager an implementation plan, not just an answer. So we might have given a whole bunch of alternative optima. The manager picks one. In this case, pick one of those Ohio. We had 3 alternative optima in the Ohio banking problem. Pick one. The manager picks one. Now, how do you help that manager implement that solution? So we can take, this happens a lot. You can take a model you use to solve to get the answer. So how do we get to the optimal 15 locations? A manager needs to know that. In a smart way, how do we do that? So here's a related problem. And it uses proxies, admittedly. You could develop a much more economically detailed model, but how about this? I know I want to wind up with the 15 optimal solutions that were in that map. You know, the 15 gray cells, gray counties. I want to get to that. Can I develop a model that tells me the glide path to get there? Well, I can get the population for each county of Ohio, right? And I know which, my model now has gone down to really a decision of 15, I'm only going to allow the 15 where I have to wind up. To the point of discussion about persistence, you wouldn't let things change all over the place. This glide path is going to lock things in once you make a decision. So I can start from those 15 counties that were in that solution and build a max cover problem instead of a set cover problem. So a max cover problem, if you're not familiar with it, just look at the constraint set 26 for a minute. It looks like the set cover constraints, but I put a binary variable on the right-hand side instead of a 1. And if I don't choose anything on the left side, the y is going to be a 0. So what this does is maximize the reach for a limited number of sites, where the reach is defined by the population of the county. And I'm going to limit, via constraint 27, I'm going to limit how many PPBs I'm allowed, okay? So how do are you with me on this model? It's a little bit different than a set cover. Set covers minimize a number. This is give me a fixed number k that I'm allowed to use, maximize the population reached. Very related problem. It's an extension of the set cover. Now I can take this and set k equal to 1 and optimize. And only over the counties that are in the optimal solution previously. And I'll find what? I'll find the county that pulls in the most population for 1, lock that in, set k equal to 2, solve again. Now I have the 2, but the old one has to stay in. That's persistence. And I'm doing this in such a way, it's not a financial objective, but I'm pulling in the population in a greedy way as I give them a schedule to follow as they roll out these principal places of business. But you can get a lot more sophisticated, obviously. You could do the price of land and all that kind of stuff, right? But this is a extension of a simple model to a little less simple model that could give you a glide path that you could really easily explain to a manager, because population is a surrogate for, presumably, for wealth. Some of the counties in the middle of Ohio are mostly farmland, and that would factor this in. So I don't know if I got all the way back to implementation, but the story here is take your model, don't just give an answer. You might have to solve multiple models, change the model some to get a glide path for the client. Now you've increased your chances of your work being implemented probably threefold because you've provided a roadmap. All right, I think this is the end. I'm just thanking some folks that have helped me, particularly around learning optimization integer programming. So these are some folks: Jerry Brown, Ted Newton, Dennis Sweeney's the guy who taught me that constraint that I want you to remember from Ballas and Jaroslaw. That truly is the single most important thing I've learned since graduate school. And Woolsey's always kept me on the straight and narrow to real problems. So with that, comments, questions? Yes?
In the Ohio banking example, was there any counties where they would say, we would never want to touch that county? I mean,
Yeah, we never want to go into that.
It would be something that you could implement easily. I don't know if you.
Yeah, and that would be easy to do in the sense that you could, if you're not going to capture it, you're also probably not going to put a principal place of business there. You could pull it out of the data set, or you could just lock it out. You can lock out the X variable, and also in the second model, lock out the Y variable so the population wasn't counted. So that you could tweak that.
Is that something where looking at the population information you might include as a little side quarter on the implementation? You know, this county, there's no population here.
Not enough to justify?
So
Yeah.
almost like you think ahead of where in the implementation phase you think, oh no, I'm looking at these 3-county areas, and there's no way that they're going to make any money there. So
Right.
suggest with this sort of meta-analysis, is that something that
Yeah, and that goes back to the original question that was asked, right? So the original question kind of assumed everything was good, and you know, we want to be open. Basically, we want to come in and be able to go anywhere we want. And as you do analysis, your point's a good one. It might be that, oh, that was actually the wrong question. Which counties matter and which ones don't? That's a different model, right? So yeah, it's a lot about how the problem is defined originally. Yes.
So I work in talent analytics for Caterpillar, and one of the struggles that I have with leadership is how to communicate a solution that has uncertainty when they want something that's 100%.
Right.
Because basically, since data science is becoming so popularized, what you're really asking people to do is to put their job on the line and trust the data. And so I can't tell them, yeah, this is 100% the solution. I think what you're doing with the cell optimization here, or the alternate solution, is kind of building like an intuitive confidence interval for your solution.
Right.
I think that's kind of what you're doing. And so how do you communicate that to leadership, saying this is the answer, I'm pretty sure, but trust it, put your job on the line.
Right.
It's going to be the answer. You could have been wrong, you could be wrong.
Good,
How do you deal with that?
Yeah, the way I've dealt with it, to be honest with you, in my consulting is through scenarios and doing what you just said, actually. First of all, showing multiple solutions, alternatives, and then showing how under the scenarios, good things or bad things could happen, and the degree to which the model says that will happen. That doesn't always pacify managers, though, because they think all you're doing is transferring the uncertainty to them, and now they're on the line, right? But that's the reality of a situation. All you can do is quantify that there might be variance in the results, which we know for sure there is going to be, right? But to what degree? And so at least it shows them, if they believe the model, that you might be able to see some alternatives and say, on the work, like if they're focused on the doomsday scenario, and they say, it depends on their risk aversion or not, right? I'm never doing that because I can't risk winding up in that position. That says that scenario would, your model says would be in a certain area in terms of loss or whatever, that we're not willing to accept that. Now, then you can pacify some managers, but I haven't found that, to be frank about it, I haven't found it to be very acceptable from managers. They want to know exactly what's going to happen, exactly what it's going to cost. But I think you have to be honest with them and say, this is what the model says, these potential things could happen, and if they say, well, you have to make the decision, then I can always walk away. I was a consultant, but if you're internal, you got a problem, Yes?
So, first of all, thank you for a great presentation. And
Thank you.
I agree with everything you said. But personally, the biggest challenge I have is getting to this point, getting the problem owners to the table, convincing them, yes, optimization can help you. That part is the most challenging part for me.
Right.
I'm wondering whether you have any words of wisdom to address that part.
Yeah, optimization is a black box for a lot of people, right? They don't understand it. And now, I guess what I would do, is, I mean, I've used examples like this in trying to get other clients. But usually the client is trying, he or she might not know this, they're trying to solve an optimization problem, but they don't know the math behind it, but they have objectives and constraints. And so if you can show them somehow in a simple example how you can quantify that and build a model around it, you can see that your goals and objectives are aligned with what they're trying to do. The other thing is everybody thinks they know what analytics is now. And so if you can capture it might not be exactly optimization the way we think about it, but I'll give you an example. I'm not recommending you do this, but just something simple like, if you have a client who's really kind of clueless, well, when you get on Amazon and you buy something, and then the next time you get on, or even while you're trying to buy something, they have these other recommended items. Why are they doing that? Well, it's because they've noticed that a lot of other people who bought this book buy these books. Well, that's fine, but why are they recommending these to me? Well, because if they can sell more books, because they know there's that correlation there, it's stuff they've actually experienced, and talk about optimization in that sense. It's probably heuristic optimization rather than math programming, but something they've lived and understand. Another one that I've used in the past, which usually makes managers angry, or everyone angry, is airline pricing, right? So I'm sitting next to you, I paid $250, you paid $750. And why is that? Well, people understand you can change prices, and that in some sense there's a best price for a given time, and how you just have to find that mathematically. So it's hard for somebody that doesn't have that mindset. It's hard. So I don't know if that's not a great answer, but that's what I've done. Try to relate it back to something they can relate to. Even routing sometimes. Like, we all have these things in our car now, or on your phone. How do I get from point A to point B? Well, there's a shortest way to do that. That's optimization. Yeah, knapsack problem. Anything else? Yes, sir.
I have a question about, what I've seen is that when you start the project, the client will give you probably n number of data sets, or very few data sets, because it takes, time
Right.
for whatever NDA. And that's not enough, because you need to make sure that your model works with different scenarios.
Right. Yeah, so once you start, like my practice was in supply chain, so I had models that I was comfortable porting over. There are only so many combinations of things that can happen. And so usually I would get a model up and running. I would use their current data typically. They just gave me current data and get comfortable with that and essentially debug the model, make sure I understood what was happening and why, and then go to that current baseline. If you go straight to the current baseline, you might have no clue as to whether or not your model is actually working, right? Because you've locked it down originally. So I would be doing a lot of optimization, make sure I see the trade-offs I think I should see. And then I would go to them with the baseline model. But it's like, there are only so many variations in supply chain design at the kind of model I was using. So I just developed like a library of different models depending on what they wanted to do. Did they include manufacturing or not? Were those fixed or not? So I built some off, a shelf of models essentially. But the tricky part is when you have something new to model, you get some counterintuitive results, and you have to figure out if it's counterintuitive because the data are somehow strange or your model's messed up. But when you use something like AMPLE, the models, in my experience, are remarkably simple. You can look at, if you know algebra, you can look at the algebra and see what's going on and have a lot of confidence in your model. You also, this happens a lot where you'll think you've modeled the problem and you'll solve it and you'll show them the first results and they'll say, well, that actually can't happen, and you find out there's some business rule that they didn't tell you about, and there's an iterative process to make sure that you get to their real system. That happens quite a bit, actually. Yes, Ishi?
So, as somebody who was in a company that optimization doesn't, you might not think so at Informs, but in the outside world, there's not the same buzz
Around prediction?
versus for machine learning, artificial.
Right.
So,
We need a buzzword like machine learning. I don't know. We'll figure that out later. Go ahead.
so at a real company, like how do you convince leaders that certain problems
Right. Yeah. You find a problem they care about and show them that you can actually solve it very fast and at a much lower production cost than going to machine learning. That's what I would do. It's interesting, this sort of dynamic between OR and statistics and analytics. So I had a call about 2 weeks ago, to your point about knowing about optimization. I was on a call with 2 PhD statisticians at a Fortune 500 company. And they had something in R. They were doing some things, but the bottom line is in the middle of their R code, they essentially wanted to solve a max cover problem I was just talking about. And they were enumerating. And so they said, this thing's buzzing along, and then it takes like 25 minutes. It wasn't that big, but it took 25 minutes of runtime to get just through that part, and then they would go on to whatever else they're doing, right? And statisticians learn optimization, but typically in a calculus kind of way. They don't, this is my experience, they don't learn math programming so much, optimization. So I said, send me that data set now, and I'll see what I can do. So it was not that big. I put it into Excel. I had to get OpenSolver, which if you don't know about OpenSolver, it's open source. You're only limited by 1 million rows and your RAM on your machine. This is the same thing. They wanted the top 15 solutions. They didn't want just an answer. But again, they were enumerating, sorting, and then taking the top 15. That's what they were doing. OpenSolver, free, right? To get the top 15 solutions was like 0.28 seconds. They just don't know about optimization the way we think about it in OR, a lot of them. So I told them, yeah, I think I can help you. Here's what it's going to cost. No. Yeah. I didn't teach them optimization. That wasn't my job. But they actually haven't replied yet to my proposal. So they probably found somebody down the hall who knows OR, and they're like, why are you talking to this guy? But anyway. Other things? Yes.
To add to your response, I think if you have somebody at the table, the biggest difference to me between traditional optimization and machine learning requires data.
Yeah.
So if they don't have the data, or they're not willing, as you said, to go through multiple iterations to learn, then closed form optimization is
Yeah. Machine learning, well, I should be quiet. It doesn't seem that the concept is not that complicated. And you can envision the same kind of thing with optimization. With real-time deployment, you're optimizing, and maybe feeding something back and re-optimizing, and maybe we need a buzzword. That's the bottom line. We need a new buzzword.
Time for maybe one more question so we can let Jeff get to his
Next session? Yeah.
Did you have anyone else? Well, this has been terrific. Thanks so much.
Thank you. Appreciate it.